All right, so welcome to part one of the kinematics section here. You'll find that this section is partially review from Science 10, and then some of it will come across as being new. So generally, people don't find this section too bad. It's just a matter of kind of keeping it all straight. Before we get into this, though, I do want to point out this. Now, this is very, very important, and this is not something I'm willing to waver on. Now, at some point, I'm sure I'll talk to you about, kind of my own university experiences and things like that. It comes up in conversation, but my first degree is actually in physics, was my major. Um, Along with that, I've done marking for university professors and things like that because in university, the professors don't have to do their own marking. The university pays other people to do it, um, which would actually be my dream world, but that's a story for another day. So I know what it takes to be successful once you get there. And then also I've been able to kind of like see the world of science probably a little bit more than you have. So this isn't something that like I'm making you do just because it's like something that's always been done. It's because there's actual value in this, and I wouldn't be doing my job if I didn't train you how to do things that have value in them within the field that we're studying. So the major focus here is not the final answer. Okay, like simply just getting to the final answer all the time and just writing that down, you would actually fail this course. Okay, now it sounds a little weird, but there's way more to it than just being able to punch some numbers into a calculator. Okay, so you need to learn how to communicate your ideas properly and efficiently. Okay, now at the beginning there'll be a little bit of lenience, but not much. If it doesn't look how it's supposed to look, like I'm giving it back to you and you're starting over. Okay, so just keep that in mind. Now, I'm not looking for like, neat writing and things like that, but I want to see organization of your thoughts and ideas. So before you just start ripping through an answer, like take a second, make a plan, and then kind of figure out how you're going to attack the question. Okay, so this goes for quizzes, tests, assignments. If you hand it in and it's like a mess of ideas all over, like you're getting it back, and when you can rewrite it properly, I'll take it in and I'll mark it. Okay. Now, there's a general template here that we're going to follow when we solve questions. It's step 1 is a formula, 2 is all your work, including units, 3 is an unrounded answer, again with units, and 4 would be a properly rounded answer. Okay. So we'll kind of exercise that and we'll see that in action as we go through some of the stuff today. Now, kinematics in itself is a branch of physics that looks at how objects move. Okay, so we're really going to be looking at acceleration, velocity and speed, distance and displacement, and time. Okay, we'll get into some formulas in part 2 of the unit, but at the beginning we're just going to hammer out some of the basics and some of the graphing as well. Okay, so the first thing we need to chat about is scalar versus vector quantities. Okay, so all numerical quantities in physics can be divided into these two categories. So scalar quantities are things that are just like a number in a unit. Okay, so for example, like mass, length, distance, speed, power, energy, work, and time. Okay, vector quantities, however, also include a direction. So sometimes the direction is important, other times it doesn't really matter or it doesn't exist. So for example, when we talk about time, time only travels in one direction. It just moves forward. There's no way for us to turn back time, or none that we've found yet. So time is a scalar quantity. Okay, as were other things, the direction is going to be important. Like for example, if I told you that 2.2 kilometers from the school, I had hidden a really fancy treasure that you could have, but you need to find it, you're going to be a long time hunting if I don't give you a direction. Realistically, there's kind of 360 degrees of different angles that you could head out from the school to do that 2.2 kilometers, or maybe it's a kilometer in one direction and 1.2 in another, and the total is just 2.2. Like if I don't give you some direction, that number is more or less meaningless. Even worse would be if I didn't give you a unit. Like if I just said, well, it's 2.2 from the school. Well, good luck. Is it 2.2 hours from the school, 2.2 meters, 2.2 kilometers, and then what direction? I mean, you're never going to get there. Okay, so units, always important, direction for vector things. So when I look at something like 5 meters, okay, this is going to be a distance. And distance is going to be scalar. Okay. When I look at number 2, 14 newtons backwards. Newtons is a measurement of force. And I see a direction. It's a vector quantity. Okay. 15 meters per second. No direction. So this is going to be speed, not velocity. And that's scalar. So note speed and scalar. Both have S's. 14.5 seconds. That's time. And scalar. 13 meters per second squared. This n in square brackets means north. So that's going to be an acceleration because of the unit. And that is going to be a vector. And we'll see later why direction on acceleration is important. And 2,000 joules. This is energy and it is scalar. Okay. So if we take a look here at this image, we can see distance versus displacement, okay? And this is something that you should have went through in Science 10. So displacement is like how far something is from its reference point. So lots of times the reference point is the start, okay? So the starting point, it's the shortest path to the end. So notice how like this green walking trail here shows the distance that somebody walked. And the displacement doesn't have to follow the trail. It cuts straight across, okay? So that's kind of the difference between those two. So the distance is kind of like how much ground something covered, and then the displacement is just like the distance basically from the start to the end point, or how far away something is from reference point. And when we give displacement, we give direction as well as it's a vector quantity. Okay. So it says a drone flies 2.3 kilometers north and then turns and flies 1.2 kilometers west before crashing. What's the distance the drone flew before crashing? So I'm going to try and, this one, on something like this, there really isn't necessarily a formula. I mean, there is, we could write like D total equals like D1 plus D2, okay, which is equal to 2.3 kilometers plus 1.2 kilometers, which is equal to 3.5 kilometers. Okay, I appreciate if you box your answers. That way I have a little bit easier time seeing them. Now, for something like this, where there really isn't a formula, I'm fine with you just saying like D equals 2.3 kilometers plus 1.2 kilometers. But if you wanted to kind of do this properly, it would look something like that. Okay, so what's the magnitude? When you see the word magnitude, the word magnitude actually just means that it only wants the number in the unit. So if you see magnitude of displacement, you don't actually need a direction. Okay, so it would be 2.3 kilometers north and 1.2 kilometers west. And then this arrow here, or put the X on, would be the actual displacement. So this is going to make a right angle triangle. So we would do a squared plus b squared equals c squared. Okay, now this time I'm going to work downwards. So I have 2.3 kilometers squared plus 1.2 kilometers squared equals c squared. Okay, and I'm going to let you finish out the math on that one. Okay, so again, work your way downwards or like left to right, but I don't want to be bouncing around all over. And sometimes people like write the formula over here, and then they like come over here and they start like putting the numbers. It's like, don't do that. Like keep it all together. Okay. So speed versus velocity. So speed is a scalar quantity that talks about how fast an object's moving, and it doesn't really matter about the direction of it. Okay, velocity is a vector quantity. So speed, scalar, velocity, vector. So that one's always easy to remember. Okay, so velocity is the rate at which an object displaces itself from a reference point. Okay, so it's not necessarily like when you think about like your odometer or your speedometer in your car, and like when you think about like how fast something's moving, you're traditionally thinking about speed. Okay, velocity is a little bit different, and it's one that you probably have little to no actual experience with at this point. Okay, so you need to find the displacement first and then divide by the time. As we're with speed, we find the distance and divide by time. Okay. Uniform motion. So when you think about like uniforms, whether that's like a sport or a club that has a uniform, those things are there so that kind of everyone looks the same that wears that uniform. Okay, when an object is in uniform motion, its motion remains constant, or its motion remains the same. So sketch a position versus time graph and a velocity versus time graph for an object in uniform motion. Okay, so we're going to have time at the bottom in seconds, and I'm just kind of making a unit up here. It could be hours, it could be whatever you want. And on this side, we're going to have position. Okay, I'm going to put that in meters. So if it's moving in uniform motion, I should have a straight line, okay, with no bends in the slope. And then we don't need a title for these ones just because they're kind of rough sketches. If we were like actually graphing some data, we'd want to have a title. So velocity, meters per second, time in seconds. Now if it's traveling at uniform or in uniform motion, it means the velocity isn't changing. So for this one, we should have a straight horizontal line. So these two graphs actually represent the exact same thing. Okay? The exact same scenario, they're just different graphs. So then the average velocity formula, or the constant velocity formula, okay, is off on the side here. Now this is one that you would have used in Science 10 when we gave you a lot of like simplistic situations where like the speed wasn't changing. Okay, I can tell when we get to the second part of kinematics when a student is struggling or not, because they try and use this formula on absolutely everything. Okay, you can only use this when an object stays at the same speed, or you have a way of figuring out what the average velocity is. Okay, for most students, they're not super great at figuring out what the average velocity is. So in your head for right now, I would just tell yourself that this only works when you have an object that's staying at the same speed. So think about like on the highway, if you set your cruise control at 110 kilometers an hour and you're driving down the highway, that would be a constant speed, and that would be where you can use V equals D over T. So you could use that then to figure out like how much time it would take you to get to like Calgary or Bow Island or wherever it is that you're going. Okay. So there's a little note here about how you use it to find the average. So feel free to take a read through that. And if you can get that figured out, you can use it a little bit later, but there's another formula that works just as good. Okay, so a person walks 1.5 kilometers north, 2.23 kilometers south, and 0.35 kilometers north, and we're looking for the person's distance and displacement. Okay, so for the distance, okay, I have 1.5 kilometers plus 2.23 kilometers plus 0.35 kilometers. Okay, again, remember that the direction on this one does not matter. So we got 1.5, 2.23, and 0.35. That gives me 4.08 kilometers. Now I'm going to check my significant digits. In this case, I'm adding, so I need to go off decimal places. I only see one decimal place here, so I need to round my answer. 4.1 kilometers. Okay, did you see how, again, I've started by saying my variable is d, so I'm looking for a distance. And then I wrote my numbers with units, my unrounded answer, and then my rounded answer. Okay. In terms of the person's displacement, vectors get arrows on top with like a half of an arrowhead. So this one up here is distance, and this one down here is displacement. Okay, anything north will be positive, anything south will be negative. So I have 1.5 kilometers plus negative 2.23 kilometers plus 0.35 kilometers. So let's just punch that into a calculator and see what we get. So I get negative 0.38 kilometers, okay, which tells me that it's 0.38 kilometers to the south, because my answer came out to be negative. Okay, so again, don't forget that direction on the displacement, because this time it didn't just ask for the magnitude, it asked for the displacement. Okay, if the hike took 3.5 hours, determine the average speed and velocity. So if I'm looking for speed, it's d over t. Okay. Now, it does tell me that it wants it in meters per second, so I can either find my answer in kilometers per hour first, and then I can convert, or I can convert everything up front. So I'm going to do one of each. So in this first one, I'm going to put everything in kilometers per hour, and I'll show you what that looks like. So the time, 3.5 hours. Okay, now actually I realized I made a mistake here. This number up here, I actually want to use my unrounded answer. Okay, so let me fix that up. So 4.08 divided by 3.5. Okay, now you can write out all the numbers if you want, but as long as you have, if this is going to become a final answer, as long as you have kind of a couple more numbers and you need significant digits, you'll be fine. And 3.5 hours only is 2 significant digits, so I got lots here. So my final answer is going to be, let me fix this up, kilometers per hour. And, oh man, this is not my question. I take that back. Not going to be my final answer because I have to do a conversion still. So from kilometers per hour to meters per second, I'm going to divide by 3.6. That's the shortcut. Okay, so I divide by 3.6, and I get 0.3238. This would be meters per second, and 2 significant digits, and my number, so 0.32 meters per second. Okay. All right. In my next one, I'm looking for my average velocity. Let's see if we can get through this without quite so many mistakes this time. Divided by t. Not sure why that turned that into an arrow. Okay. So again, notice I've got my arrows for the vectors. So I have negative 0.38 kilometers. Oh, I said I was actually going to convert this one first, so let's do that. So 0.38 kilometers. Okay, if you think about what that would be, we're going to be looking at 380 meters. Now, I'm all right with you doing these conversions that I call like easy conversions. So like kilometers to meters, meters to kilometers. Like most of us are pretty good. We can just kind of jam that into our calculator. I'm okay with you just doing that one. Same with hours, like 3.5 hours times by 60 and times by 60 again. We get 12,600 seconds. Okay, so if you don't write that down, I'm okay with that. So we have 380 divided by 1,002. So 12,600, sorry. So we end up with negative 0.03015 meters per second. And then 2 significant digits again, so negative 0.030 meters per second. Or if you wanted to, you could go to scientific notation. You'd have negative 3.0 times 10 to the negative 2 meters per second. Whichever one you feel more comfortable with will work. Okay, so I'll let you go through example 2 on your own, and then you can also give 3 a try. So 3 is going to require a little bit more thought. So you might have to think about how you're going to come up with distances and displacements to come up with speed and velocity from those separate situations, but we'll see what you can come up with. Okay, and then that's kind of where we're going to stop for today. So next day we'll go through what the answers to these couple examples are that I left you with, and then we'll go through the graphical analysis stuff, and we'll be moving forward through the rest of our kinematics unit. So best of luck, and we'll see you all tomorrow.